Hello, curious people. In this lecture, we'll learn about motion, 1D motion in more detail. Mainly, we'll be learning about uniform and non-uniform motion, uniform, non-uniform in terms of velocity. So your curiosity over uniform, non-uniform motion will finish after this class, this lecture. So how do we represent motion? We touched base on this in previous lectures already. We define a coordinate system, and generally along x, east-west direction, we call along x, like in this figure here, first figure. And we define position along x, and we show velocity with a vector. If velocity is going to the right, we take it as plus, bigger than 0. And if it's to the left, it's minus. We could also have up and down vertical motion. Up is plus, down is minus. That will be general convention for both position and velocity. And acceleration, we'll get there, is also a vector. We also talked about representing motion. I want to talk about a little bit more about this in this lecture. We'll get back to it, but mainly we'll focus on using the representative motion to make a graph, motion graph of position versus time, as you see in this figure, or velocity versus time. In this motion here, we have a person, let's say, moving, and we take a picture of him, her, at different times, and we see its positions, right? x1, x2, x3, and so on and so forth. As we list those positions, we see that time is equal to 0. Time is in minutes, by the way, here. For the sake of simplicity, we'll leave it as minute. But remember, a SI unit is second, so we always will convert to second in the following lectures. Position is in meters. So 0, 1, 2, 3, 4 times. Here are the positions listed. If we want to make a graph of that, how do we do it? At t is equal to 0, x is 0. So for a graph of x, position versus time, t, we draw our axis lines. We take x as a vertical, t as a horizontal line. And we know at t is equal to 0, position is 0, so we put a dot there. At t is equal to 1, position is 60, then we go to t is equal to 1 somewhere here, right in the middle. This is 2, this is 0, and position is 60, it comes to somewhere here. So we put a dot at the point where we draw lines from 60 along horizontal and lines from 1 along vertical, and where they intersect, maybe I'll use red here to make this more clear. Where they intersect, we put a dot. Let's do one more at time 2. It's 120. We go to 2, draw lines, and where from 120 also we draw horizontal lines where they intersect. We put a dot. And we keep doing the same, putting a dot everywhere we have a value of time versus a value of the distance, and so on and so forth. And we will see all these dots going along. And we have a graph. We have how position changes as the time passes. To understand this better, we can draw lines connecting those dots, and you guys will be doing this quite often in labs in this lecture. And we see an increase in trend here in the first part, right? In the first part here. Let's divide this into 3 parts actually. If I call this section 1, this section 2, and section 3, I see all increase in trends here. Section 1 position increases, section 2 it slightly increases, it increases a lot less than 1, and then it increases in section 3 significantly. That's how I read my graph, first of all. Second of all, so I can say that this car moved, increased in its position quite quickly, first 3 minutes, and then it increases slowly up to 6 minutes, and then it increases its position even faster, 6 to 9 minutes. I understand some stuff from this graph. I can also find additional information from graphs, which is often possible in physics. First one we will learn, we also touched base on previous lectures, is that slope of this graph is equal to the velocity. So I'm going to show it here. Slope is equal to the velocity of this graph. Wait, we're not showing velocity yet, never mind. How do we find the slope? We have lines, and we look at, if you guys remember, we look at rise, find that. We look at run, and slope is equal to rise over run. And again, it will be equal to velocity of the object, the moving object. And we can also define the direction of this motion using slope. So slope is equal to velocity. This is still holding. Only this graph is not the slope graph. It's just showing how to find the slope better. We can check what has happened to velocity by checking the slope. We have a slope here. Smaller slope, less steep. So that means if I call this velocity V1 and this V2, V2 is smaller than V1. So the car was going faster, now it's going a little bit slower. If I look at the V3, it's even going faster now. So if I want to maybe rank the velocities, I can say that the largest is V3, and then V1, and then V2. That's a very good information there. I can also determine the exact value if I know this rise and run values. And we know them, right? We know these values from the previous table. We can exactly see which one is which one, or quite often or most often what we will have is what is the value there and what is the value here, and so on. And we'll find that rise over run, and it will be our velocity. This tactic box, I want you to come back to read and review whenever you are a little confused, maybe about how to find velocity using the position versus time graph. First of all, we can determine the position by just drawing lines from, for example, what is the position at time 2, as we did in the previous page. Draw a line from time 2. And draw a line from x-axis where they hit the x-axis. This is a point along the path. This would be what the position x corresponding to time 2 is. Second of all, you can determine velocity at a time, define the slope at that time. For example, what is the velocity at point 4 and time 4? Is the slope of this line in this region, which would be velocity 2 as we show up there. And the direction of motion also will be determined from slope. If I have a positive slope, if slope is positive, that means velocity is positive as well. And if this is an along horizontal motion, is towards plus x, right? Plus x direction or east. I can describe my velocity direction of motion using the slope. Uphill tilted slopes will be positive, so in this case all the slopes are positive, and downward tilted slopes are negative. So here we all have positive slopes. That means the car, the object, is moving always to plus direction. If it's along x, right, to the right, right? If it's along y, it would be to up. from the information of how the velocity, by the way, our book is defining velocity along x to be vx. Since this is 1D motion, we can always go ahead and call this v, keeping in mind it's along x or along y, or we can keep it vx. If it's along x, it's vx. If it's along y, it's vy. So keep that in mind. From the graph's slope, I get it. I get velocity, rise over run, and that will be delta x over delta t. And delta x is always the final position minus initial position. That's what delta means. Delta t is also the same, final time over initial time. But we will always or mostly have initial time to be 0 seconds. We'll set the final time to t, and we will replace this thing by t. Keep that in mind as well. It's delta t, only initial time starting at 0 second. Anyhow, so this is slope, this is velocity. And using this equation, I can derive a new equation. And the new equation is, so from here to there, I can write this, right? I can multiply each side by delta t. Delta t cancels here, and I'll have delta x on the right is equal to vx delta t. Always holds. I can also put here delta x is equal to x final minus x initial. That's equal to vx delta t. And then this guy goes to the other side as plus, so I can also find this equation. So all these three equations can be used to solve for values in uniform motion. And again, uniform means in terms of velocity, so it has a constant velocity. Let's think about this a little bit. Constant velocity, right? Slope is equal to velocity. So that means whenever I have a position versus time graph with constant slope, right? If the slope is constant, that means I have a uniform motion. Velocity also will be constant. Constant slope, constant velocity. So I'm expecting to see straight line graphs for a uniform motion or constant velocity motion. Here's a nice example. Find the car's velocity from its position graph. Here's the position versus time graph for a car. Draw car's velocity versus time and describe its motion, what it is doing. Let's look at this thing over here. What I'm gonna do is draw lines. They won't be perfect lines, but overall they will show me what are the values. And I'm gonna call these section 1. This will be my section 2. And this here will be my section 3. And I know I find velocities from slope. So velocity is equal to slope. Simply rise over run. And I'll keep that up there. So in each section, I'm going to have a different velocity. And overall, I can see that in the section 1, I have a constant velocity. And I'm going to call this V1. Let's put it here actually. So with section here, we have V1. And here we have V2. And in here we have V3. It's a constant velocity. Section 2, I have a 0 velocity. Let's write down 0. So V2 is 0, our velocity 2 is 0. Section 3, I also have a constant velocity. Without doing any calculations and so on, I can see that. So V3 is constant, V1 is constant, and V2 is 0. So I'm expecting to see a graph of straight line. Let's make this thinner. Let me draw my XY coordinates. It won't be perfect, but always draw an ugly picture. X and Y. The arrow is unnecessary actually. Let's remove the arrows. And let me also think about if the speed velocities are positive or negative. If I look at this slope here, this slope is negative. Remember, it has a downhill. Look, it's downhill. This one is 0, we decided, and this one is positive. Now I am all ready to qualitatively show my velocities at each section. Overall, I am going to show my sections here too. This is my 2. This is again time. And now it will be velocity. Unit is meters per second. And section 2 and 3. Section 2 starts at 2, ends at 4, and 3 ends at 6, starts at 4. So I am expecting negative velocity constant, 0 velocity, and a positive velocity. Looks like the third velocity would be larger than the first. V3 would be larger than V1, but I'm not sure. I'm going to calculate that. And the values there would be V1 here. That guy is 0. So this would be V2, 0. And this value here would be V3. Let's calculate the values. I'm going to say V1 is equal to slope 1. And I'm going to look at the rise over run for this slope. If you look at rise, I decided that it's negative, so I am good. I'm only going to look at the magnitudes here. I see that rise, this would be my angle here, by the way. So the rise would be here for my slope. I can also show it over here. It's 4. I can also take minus 4. Again, we know it's negative. We can drop minus, but let's take it minus 4. Divided by run, which would be this over here, 2. So it's minus 2 meters per second. That means it's negative. So that thing here is minus 2. Let's put it here. That's this point over here. Then we have 0. Then over here on the right, I have to decide what is rise over run. I put too much in here, but I hope you guys can see. This should be about 6. I didn't do a good job here. So the rise is all this value. Alright, what I can do is just to look at, again, I decided this is positive. I can just look at how much is this, or I can say, set my x initial, x1 final, or x1x, not x, this is y, y1, y2, and look at the difference. And then set x1, x2, right? And look at the difference. So I'll do a little bit keep in here 2 slope 2 will be, this is my rise, it's y2 minus y1, it will be 10 overall. 6 minus 4, if you guys want, I'll write it maybe. I know you guys like putting everything in mathematically. I can see this is equal to 10, but let's go slow. So 10 meters over time. Here we have 6 minus 4, 2 seconds, right? Run is 6 minus 4. So 10 meters over 2 seconds, which means 5 meters per second. So this value will be here, 5. Here's my graph. How can I describe this motion? I can draw a line and show it, imagine it. We have to do a lot of imaginations here. I'm gonna quickly try to describe it here. So if I draw my X line, right, this is my X to the east, my car starts at 0. Let's use another color here. Starts at 0, goes backward a little bit, so I have to extend this a little bit actually. Let's say I have my car here. This is really an ugly picture. It goes this way a little bit. How much? 2 seconds, right? 2 seconds here. Then turns back up to about, I don't know, 4.9 seconds. No, not sorry. Up to 4 seconds it goes, it's 0, it stays there. Then turns back and goes up to 6 seconds, it goes further. I'm gonna assume it came here. We didn't really look at how much distance it traveled exactly, but overall description of motion is complete, and it starts here, goes back a little bit. We can see how much it moved. We can put that too, right? -4, and then comes back, passes 0, right? And then reaches to 6 meters. Let's put them actually. So this is 6 meters, goes back to -4. Everything is now described, and I know how much speed it is. It stays here a little bit and then turns back. It's all clear. And this page summarizes it, assesses it. Always think about if your so after you solve, you go back and check if your solution makes sense. What I would do is check the slopes again, make sure if they are negative. So my velocity is negative, 0, so my velocity is 0, and so on. This one is a quick check. Look at which velocity versus time graph goes with the position graph. To solve this, we look at, of course, slope and how the slope is changing. Increase in slope means increase in velocity. Decrease in slope means decrease in velocity, and so on. If we have an uphill slope, uphill is positive, right? Positive slope. And if we have a downhill slope, it's negative. So these are the information. Overall, we'll look at the slope. Let's see, I'm gonna use yellow here. From here to there, as you probably can see, I have a straight line. That means I have a constant slope. Oops. Constant slope means constant velocity, right? Constant velocity here. If I look at like from there to up to here, and I draw, let me pick another color now. I'm gonna make my line. If I draw maybe 2 lines of tangent lines. Let's make that straight. One here, maybe. One there. First of all, one thing I forgot. Slope is uphill. So this velocity will be positive, right? Still here I have an upward slope. It's positive. Let's call this actually velocity 1. Let's call this V1. Go back to my pen. V1. Here I have V2. It's positive because upward slope, and it's decreasing. Why? If I look at the first and second lines I draw, second one is less steep. This guy is quite steep. This guy is less. If I draw one more, I don't want to make it really too much cluttered. I will see that this guy is even less. So decreasing. I'm expecting a decrease in speed in the section 2. Section 3, obviously. That velocity decreases, and as it comes to here, let me draw a line again here. Somewhere here, I see that it's straight line, maybe a bit later, exactly straight line, 0. So in the section decrease, and then we have 0 velocity. I'm gonna take that guy maybe. Either I should put it in the other section or just delete it. Alright, so here velocity 3 and it's 0 because we have like a level slope, 0 slope, parallel to t-axis, horizontal. So if I look at the graphs, first I'm expecting a constant line. This is a constant line. This is a constant line, right, in the first section. But this guy is negative, so it's not correct. That's correct. The rest should also be correct because there's no other options giving me a constant line. But let's continue. Later on, velocity decreases. Should be getting towards down to 0. I see that in here. And then for a while it's 0. So it should be C. This would be a type of conceptual question we might be seeing in this section. Position graph at 1.5, which would be somewhere here. What would be the velocity of this object? Now I see in all this section here, we have a constant velocity. We call it V, let's say, constant. So I can find that slope, which will be this rise over run. And I know rise over run, I'll find it. So V is equal to slope. I see directly it's 20 minus 0, right? Meters divided by 2 minus 1 second. So 10. Oh, no, sorry, not 10. 20. 2 minus 1 is. Oh, 2 minus 1 is 1. Yep. 20 meters per second. 20 over 1. So that's our answer. We could think about if it is positive or negative. But we don't have to. There's only one answer. It's positive, but it's positive. We can also see, right? It's uphill. Uphill, positive. Let's put it in here. Uphill. Positive. This is downhill. If we are asked to find this one, it would be negative. Let's rewrite that. downhill, negative, smaller than 0. So hope you guys are on board with finding the velocity using velocity position versus time graph. We can also go from velocity to position. Simply, if I have a velocity versus time graph, area is equal to position. Here's my equation. And we already got this in the equations part, right? We had Vx is equal to delta x over delta t. And now we are seeing that delta x is equal to Vx over delta t, which is actually this area. So that's where the equation also, we can say, coming from. An example here. The figure below shows the velocity versus time graph. As you see here, for a car pulling away from a stop, it's increasing its velocity as expected, right? It all makes sense. How far does the car move? Just this area. And this area is found as it's a triangle. It's this side times that side over 2. So for this case, delta x will be equal to area, which is equal to 12 times 3 over 2. You can simplify it by dividing 12 by 2, 6. So it's 18 meters. Simple as that. Velocity versus time graph. This is a quick check again. At time t is equal to 2, what is the position of the object? Assuming it starts from x is equal to 0. I can always imagine, let's say this is a car going along x. Starting at x is equal to 0. This is x direction. My car is starting. I'm going to draw my ugly picture now. I have its velocity, and I'm going to check after t is equal to 2 seconds. T initial, I'll take as 0. I'll call this t final. What is its position? It's this area. And as we can see, this is a rectangle. Delta x displacement is equal to 4 times 2, 8 meters. How much it moved is this displacement from its original position. So that means since it started at 0, delta x should be that, and x final should be 8 meters. All right. So let's recapture the slope at a point of a position versus time graph. An object is the velocity of that object at that point. The area under velocity versus time graph an object is the displacement of that object at that point. That's all about the uniform motion. Non-uniform motion, again in terms of velocity. Now we don't have a constant velocity. Velocity is changing in time. We'll investigate that. And first, if we investigate x versus t, position versus time graph, it won't be a straight line, it will be a curve, as you see in this picture. We can find the velocity at any moment in time, and it will be changing. And how we find it is at any point we draw a tangent line to that point. So if I want to find the velocity at this point, I draw a tangent line there. Change that to a different color. Let's say I want to find the velocity here, I draw my tangent line. Let's say I want to find the velocity here, I draw my tangent line there, and so on. And then I try to find how I can find the slope of that line. What I can do is, if I can define some points like we did in here, right? I can define this and that point, this and that, and then I can find rise over run. This would be my run, and this would be my rise here. and I can find the velocity at this point. That would be the velocity at this point over here. And the velocity, since the velocity is always changing, now we will have description of a new velocity. We'll call that instantaneous velocity. Velocity at a certain moment of time. And the velocity I find from here, we instantaneous, it's going to be inst, equals the slope at that point. What is the point? Point at which I draw my tangent line. So it will be t is equal to 4 for this graph. Still I can have a very weird looking velocity. This graph here is velocity versus time graph of a lion that is attacking its prey. It's curving, not even increasing steadily. Still area under is equal to delta x. That still will hold. If I can find a way to calculate that area, I can calculate how much displacement this lion has. Alright, we have x versus t graph here for two different objects, 1 and 2. Do they ever have a same velocity? Now this guy is a constant velocity, right? If I look at the slope is constant. Let me do a better job here. That's red. Alright, slope is constant for this guy. Slope is equal to velocity, right? And since slope is constant, velocity is constant. So constant velocity here. And slope is, as you see, but for 1 it's not constant, right? It's curving. So I'm going to draw tangent lines throughout to see if at any point it could be that my tangent lines are parallel to, this is too much, I should maybe curry it down a little bit if I can. Alright, I couldn't. Alright, here we go. And I can see that here, let me redraw that line. I can see that this line is pretty much, maybe I didn't do a perfect job here, but pretty much parallel to that. So they have the same slope. That means some point definitely these two have a same velocity before t0, which is the answer here. At some instant before t0, they have the same velocity. This quick look is also a very nice question. So we have an x versus t graph. It's curving, so definitely we have a non-uniform motion. Slope is changing everywhere, so velocity is changing everywhere. And from this point on, we're talking about instantaneous velocity, because non-uniform motion velocity always changes. There's no constant velocity. We are looking at instantaneous velocity. Velocity at a certain moment of time, at point A, for example, B, and so on. A car moves along a straight stretch of road. The following graph shows the car's position as a function of time. At what point or points do the following conditions apply? Displacement is 0. I can simply read values of displacement. First of all, I'm going to make this, alright, let's undo that. First of all, this is 0, right? Okay. This dude is 0. So x is 0 here, t is 0, we start here. At a, x, this is the t value, let me call this ta. And this is the x value, xa. It has a positive position at point A. And I can keep following like that. I can define the time and position at any point I see on this graph by drawing lines to x and t axes and see where they hit the axes, right? As I keep going like that, I will see at D, there's the time bigger than 0, td, but x is 0. So at D, the car apparently goes somewhere and then comes back to 0. I can read that from graph. This is also a very important skill we can have. So displacement is 0 at point D. Hope that makes sense to you folks. The speed. For the speed, I'm going to look at the slopes. I'm going to draw tangent lines to guess. From A, I see speed is decreasing, and at B, exactly at B, I see a line parallel to horizontal line. That's 0 there. So my answer is point B. The speed is 0 at B. Is there any other positions I'm seeing that? I'm going to keep drawing my lines to see. Now I have negative slope at C. Consider that. And steepness is increasing. At D still have a steepness. Now I see a decrease here, right? And look at E. It's also 0. So that should be B and E. Oops. Speed is increasing at C. If I look at the C point, let me get the red here. At here and a bit later, I see the steepness is increasing, slope is increasing. I'm going to use this up arrow for increase, and that means velocity is also increasing, so C. Speed is decreasing, we already said A, and after we see the slope is decreasing. And that means velocity is also decreasing, so the answer is A. Very nice question. All right. Since we have change in velocity now, we have a new definition, and it's called acceleration. It's simply rate of change of velocity. Remember, velocity is rate of change of distance, acceleration is rate of change of velocity, and I can find the acceleration using this equation. Change in velocity over change in time. Now, I put it here. And again, we're assuming and imagining motion along x, so we're calling this ax. We can also call it a, but imagine when you see ax or vx, always imagine motion along x. I'll take this guy over here. So assume somebody is walking along x. All right. And thus we are defining everything in terms of x, ax and vx and so on. Distance is also x. If the a acceleration is this value here, we can guess that from the slope of velocity versus time graph, we can get the acceleration. So that's a new information here. Slope of the velocity versus time graph, which will be rise over run over here. This would be my rise again, right? And this would be my run. That's my acceleration. Notice, if I'm calculating the acceleration for this part, it would be negative because slope is negative. I'm already getting some information, right? I'm already getting some information. I'm gonna, oops, not that. Erase this guy over here. It's making it confusing. All right. And again, we call it ax because we assume motion is along x. That's all. Very similar to going from position versus time graph to velocity versus time graph. We can go from velocity versus time graph to acceleration versus time graph, looking at slopes. Constant slope, uphill, positive. Constant acceleration, positive. Exact value equals the slope. Zero slope, zero acceleration. Constant slope, negative, smaller than the first section. Constant acceleration, negative. And I can draw my acceleration versus time graph using that. Here is a simple example. Lions, like most predators, are capable of rapid starts from rest. A lion can sustain an acceleration of 9.5 meters per second. I will always tell you to stop here and think about what's happening so far. What do I know? I have the solution here already, but I'm going to go through it slowly with you folks. So I'm going to draw my lion. I have a lion. Yeah, that's my lion. It's a male lion, so it has hair. And it's trying to catch, well, actually female lions hunts, but let's say this is the male. And the male takes care of the kids. All right. So a lion trying to catch a prey, and it can accelerate. So it will be starting from 0, right? Some information here. My initial speed will be 0 meters per second. And it will accelerate to another speed. Final speed. I'm not sure if I know that yet, but I know from here to there what the acceleration is. Let's go with the book. Let's call it AX, and it's 9.5 meters per second squared. That's the unit for acceleration. How much time does it take a lion to go from rest to a typical recreational runner's top speed? 10 miles per hour. So how much time would it take? That's what I'm asked. That's what I'm understanding. And I'm understanding that it's gonna reach this speed. What would that be? That would be my final speed. 10. I like showing miles per hour like this. It's more informative, so I'm gonna call it that. Alright, so how do we find that? First of all, I have this idea. I want to go with SI units. So I'm going to convert everybody to SI units if they're not. This is an SI units. Remember, SI units is meters, kilograms, seconds, right? This is distance. This is mass, and this is time. So AX is fine. It's SI units, but we final. We initial is fine. It's 0, whatever. Everything is 0 there. We final. I have to convert that. I'm going to convert that to meters per second. That's the SI units, and it's given to me here. So that tells me that I can multiply my number by 1 mile per hour over 0.45 meters per second, or 0.45 meters per second over 1 miles per hour. Since I'm going to cancel miles per hour, this would be the one I want to multiply with. So I'm going to convert that first, and I'm looking for time. I go check my notes and I will see this. I'm going to look for an equation that relates speed, velocity. Speed is velocity without direction. We can say speed, but keep in mind they are not the same. Time and acceleration, it's that for non-uniform motion. Alright, non-uniform motion. And I'm looking for delta t. My short version, folks, is to switch these. It always works. You can switch these too. So this gives me that. It's equivalent to multiplying each side by delta t. Okay? And you will have this delta t. Then divided by ax. So 2 steps comes into 1 step in this case. Delta t is equal to delta vx over ax. You see that here too. It's only given without much showing how we get there. Alright. So I'm going to use this equation. insert my value and insert my value in SI units to find my time in seconds, which is SI unit. So first of all, I'm going to convert my speed. Here it is done. It ends up being 4.5 meters per second. Insert it in here. I already know my A as well, and calculate my T, delta T. 0.47 seconds. So it took this line 0.47 seconds to reach that speed and catch that prey. Direction of acceleration is also important. Here's a little bit of technical stuff. Well, the book showed V here as just V, not Vx. Cool. If I have a speed to the left here and it's changing, the motion diagram shows a particle that is slowing down. I have a large speed, let's call this V1, and then V2, and V3, and V4. The sign of the position and the sign of velocity are. So sign of velocity is obvious, right? It's going to the left. This is plus x. This is minus x. Sign of velocity is to the left, so it's negative. Sign of the position, for the sign of the position, you folks look at here. And check those positions, right? This is x1, x2, x3, x4. They're all positive. So position is positive, velocity is negative. But I want to tell you one more thing here. Acceleration is also shown in here. And how do we find the acceleration? As we see, as the object is slowing down, decrease in velocity vector's length to the left, negative, right? Acceleration is on the other direction, constant. We see the same length here, and positive. If an object is slowing down, I have this note here, acceleration and velocity are in the opposite direction. And we can quickly check why that is. Acceleration is equal to change in velocity over change in time. Time is a scalar. Acceleration is a vector and velocity is a vector. So from any step to any step I can check that. And the direction of change in velocity, if I have an equation this sort, again it will be a little bit technical, but the direction of acceleration is equal to direction of change in velocity. If we have an equation like this, vector on the left side has the same direction as the vector on the right side. Scalar doesn't show any directional effect. So what does that mean? Is direction wise I can check the direction of acceleration by looking at the direction of velocity change. Let's say V1 to V2 I'm looking at, right? V1 to V2. I'm going to the left, so V1 would be my V initial, right? And V2 would be my V final. And delta V is equal to V final minus V initial. This would be also a very nice vector subtraction review. I'm going to draw my vectors. V final is V2 to the left. So let me draw it here. The length is not to scale. Don't worry about that. This is my V final, which is V2. Minus V initial would be a vector that is equal in length, opposite in direction to V initial, which is minus V1 here. So it will be the same length of V1 to the right instead of to the left because it's minus V1. what would that bring? And if I do head to tail addition, I take my minus v1, start it from the end of v2, my final velocity, and draw it. And I know minus v1 in length is a little bit larger, right? My speed is decreasing, so my velocity is decreasing. My velocity is decreasing. And v1 is a little bit larger than v2. Now head to tail, I take the first vector, draw it, take the second vector, carry the beginning of it to the end of the first vector, draw it, and the resultant vector, which is A, start from the beginning of the first vector and it directed toward the end of the second vector. Let me draw it again with a different color here. Oh. Okay, I'll use blue. This is my A. Now this is showing the direction-wise. What is the direction of A? Of course, its magnitude will be not equal to that because we divide by delta t. But it shows us that if the velocity is decreasing to the left, acceleration is to the right. We proved it, and that's why that is the direction of acceleration is in the same direction of change of velocity. I know this is a little bit too much, too detailed, so we have a summary for you. And our book nicely summarizes that. Sign of acceleration is defined using this nice box here. The velocity and acceleration has the same direction. If an object is speeding up, it could be speeding up left, speeding up right, up, down, doesn't matter. If an object is speeding up, its acceleration is in the same direction of its velocity. The velocity and acceleration has the opposite direction. If an object is slowing down, doesn't matter up, right, down, left, always opposite. If an object is slowing down, its acceleration is opposite to its velocity direction. These are also showing us examples of velocity diagram. Increase in velocity, same direction. Decrease in velocity, opposite direction. Now increase in right, decrease in left. Right? But accelerations both are to the right because one is in the same direction, one is in the opposite direction. Decrease in speed to the right, acceleration is to the left. Increase in speed to the left, acceleration is to the left. So always come back to this box. So decide the direction of acceleration, knowing the direction of velocity and if the object is speeding up or slowing down. We can also look at the slope of the graphs. If we can correctly define the graph of an object that is speeding up in positive direction, it would be this. Slope is positive. Slowing down in negative direction would be this. Slope is positive. Remember, uphill. Uphill is positive. Uphill slope equals positive. And the slope also gives me the acceleration, so acceleration is also positive. Similarly, positive decrease in speed. Graph is this. Downhill, slope is negative. Negative increase in speed. Graph is this. Downhill, slope is negative. Slope is negative. Acceleration is negative. All right, there are some more questions here. Quick checks. I'm going to leave these up to you to review. Just this one I'm going to do. This is taking longer than I planned. This person is jumping on a trampoline at the minimum down position. Let me read it. At the very bottom, where the sag is the greatest. That means you're going down, still pushing down with your velocity, but your velocity is decreasing, right? Because you're going to stop a bit later, and then you're going to start going up, but you're still going down until the maximum position. you're slowing down, your acceleration is in the opposite direction. Oops, it should be an A. So at the bottom where the sag is greatest, acceleration is upward. Let's actually quickly go over these. Cart is slowing down to the right. So if I draw its velocity diagrams, it would be getting smaller and smaller and smaller. Acceleration should be in the opposite direction, right? It should be I, and that should be V. What do the velocity and acceleration graphs look like? Positive decrease in velocity. I should have velocity starting at a value and decreasing. Not necessarily to 0, I don't know that, but let's say this one is a possible result, this one is a possible correct answer for velocity, right? This one is not, because it's increasing velocity. This one velocity is negative increasing, we don't have that. So D and A goes, either B or C. Acceleration should be negative. B says it's positive, so it can't also be B. Should be C. Negative acceleration, positive decrease in velocity. This question is already solved for you if we know graph of velocity versus time graph of a rocket. Can we find this acceleration? If it's a constant acceleration, we have a constant slope, as we see here. Slope is equal to acceleration. That's it. And here's the acceleration. Following summarizes what we talked about. Starting from this equation, we can define new equations, and we can use all these equations. Defining final speed, known initial acceleration and time, or one unknown here can be solved. Defining final position, known acceleration, initial velocity, and initial position and time. And or finding a value of final speed without the time, we can use this equation. And we're going to look at some examples later. See you in the next lecture.